Hello, fifth graders. We are going to continue to talk about the all-important concept of the equivalent fraction. What I have up here is a number line that goes from 0 to 1, and I've already created a halves number line by putting a point midway, the midpoint between the 0 and the 1, creating two equally sized pieces. So this is not a tooths number line, because that would sound weird, but a halves number line. This is the general formula, of course, that you were introduced to in a previous video, that if you have a fraction a over b, it will always be the same point on the number line as a times c over b times c, where this c and this c, of course, are the same number. And neither the b nor the c can be 0 because we can never have 0 in the denominator. This is the general rule. What I'm going to do now is to continue repeatedly cutting pieces in half. And when you cut a piece in a line segment in half, of course, you only need one point in the middle to do that, which I already did. But let me do it again to each of the halves that are up there. Let me divide each half into two equally sized pieces by putting a point in the middle. So a point here and a point here should do the trick. That should look, if I've been careful about measuring, those points should look now as if they have cut each half in half, right? That point is halfway between 0 and 1/2. That point is halfway between 1/2 and 1. But of course, if you look at the entire unit length from 0 to 1, we now have 4 equally sized pieces, right? And let's count them. Of course, 0 can be considered as 0/4. This point here is the first fourth to the right of 0, so it's 1/4. This point that was originally 1/2 is now the second fourth, so it's 2/4. This third fourth to the right of 0 is 3/4. And the number 1 is the fourth fourth. It was earlier the second half, 2 halves, but it's now 4/4. And of course, the general rule is that if you have a fraction where the numerator and denominator are the same number, the fraction is equal to 1. 17/17 is 1. Okay. Let's just count those fourths and make sure we see that the fourths number line has divided the distance between 0 and 1 into 4 equally sized pieces. We can go 1, 2, 3, and 4, and those little jumps that I made with the marker sort of point out to you the 4 equally sized pieces that are the fourths number line. Well, how about if we do the same thing again? How about if we divide each fourth into 2 equally sized pieces by putting a point midway in the middle, right at the middle of each of these fourths line segments. In other words, we put a point here and here and here and right there. I've put a point halfway at the midpoint of each of those fourths number line segments, right? Right in the middle of that fourth, right in the middle of that fourth, right in the middle of that third fourth, and then also right in the middle of that fourth fourth. What kind of a number line do we have now? How many equally sized pieces do we now have between 0 and 1? Let me get rid of these. I hope you agree that we now have 8, right? We now have 8. But before we count and name those eighths, let's just make this observation. We have a pair of equivalent fractions right here with 1/2 and 2/4. And I think you all know that 2/4 is the same as 1/2. The big lesson that I want you to have now as fifth graders is that 1/2 and 2/4 are equal because they are the same point on the number line. What about in terms of this formula with the A, the B, and the C? Well, we can see the A over B here as being 1/2, and then the C is going to be 2, right? So over here, 1 over 2 is going to be equal to 1 over 1. There's the A and the B, the 1 and the 2. And now C is 2, so we'll go times 2 and times 2. The C here and the C here are each of these 2's. And of course, 1 times 2 is 2, and 2 times 2 is 4. So 2/4 equals 1/2. And the fact that the C is 2 here is because when I created the fourths number line, I divided each half into 2 equally sized pieces, right? When I had the halves number line, there's 1/2 right here. I put a point here and created 2 equally sized pieces. And I put another point here and created 2 equally sized pieces on each of the halves. Those 2 equally sized pieces on each half is what that 2 is there that I'm calling C. I didn't have to make it 2 equally sized pieces. I could have made 3 pieces, 4 pieces. What I'm doing in this video, however, each time I divide a line segment into pieces, I'm always going to divide into 2 pieces. And I have a particular reason for doing that, which I'll share with you at the end. All right? So for the rest of the way, I don't think I'll point out that the ones, the equivalent fractions that are equal to 1. We'll just cover that in the general statement that when the numerator and denominator are the same, the fractions equal to 1. So we're actually going to get 8/8 and 16/16 over here, which are going to be 1, but we won't really comment that much about those anymore. So other than 1, so far we just have these 2 equivalent fractions, 1/2 and 1/4. But I've created an eighths number line also. And let's count them out now. The 0 can be thought of as 0/8. The first eighth to the right of 0 is 1/8, and then 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and the whole number 1, of course, is 8/8. Let me again use a little loop with the marker to point out the equally sized spaces. There's 1, 2, 3, 4, 5, 6, 7, and 8. The distance between 0 and 1 is now divided into 8 equally sized pieces, so it's an eighths number line. What other equivalent fractions do we discover? Well, equivalent fractions are equivalent because they are the same point on the number line. So how about right here, 1/4 and 2/8. There's one thing about this lesson. There's a good reason to do this, I think, but there's a limitation to it. The limitation I want you to understand is every time I'm dividing a line segment into pieces, I'm always choosing to make 2 pieces. And again, it doesn't have to be that way, but we're just going to go with this. So now we see these 2 equivalent fractions, 1/4 and 2/8. Well, we can think of, in terms of the formula over here, we could think of the fact that we multiplied the top and bottom here by 2. If you multiply the top and bottom of the 1/4 by 2, you'll get 2/8. 1 times 2 is 2, 4 times 2 is 8. So they're the same point on the number line. And once again, that 2 is C. throughout this video, the C is going to be 2 because that's what I've chosen to do, but it doesn't have to be. Okay, so 1/4 is 2/8. How about here? Now we have 3 equivalent fractions. And you know what? I just said this, the C is always going to be 2, but if you go from 2/4 to 4/8, the C would be 2. But if you go all the way back to the 1/2, let's consider this. When I divided the number line into 2 equally sized pieces, and then 4 and then 8, if we just consider the 1/2 and the 4/8, right? What do you multiply the top and bottom of 1/2 by to get 4/8? Well, it's 4, right? So I guess we can see that there are C's here. By C's, I'm referring to the C's in the formula, other than 2. We get a C of 4 because it resulted from 2 divisions into 2 equally sized pieces. We cut it in half, we cut it in half again. 2 times 2 is 4. So there is the equivalent fraction 1/2 and 4/8. And how about making this observation? I think it's early enough or to do this. I think we can do this at this point. Let's say you have a fraction and the numerator is 1/2 of the denominator. Okay? It's true of all 3 of these. 1 is half of 2, 2 is half of 4, 4 is half of 8. You might wonder at this point, is that a general rule? And it is. The fact that if the numerator is half of the denominator, the fraction is equivalent to 1/2. So 50 over 100 is 1/2. 500 over 1,000 is 1/2. Well, we could take the 1/2 and multiply the top and bottom by 500, right? If you take 1/2 and multiply the top and bottom by 500, with each of these C's being 500, 1 times 500 is 500, 2 times 500 is 1,000. Just to clarify something from before, when we had the halves number line and we multiply the top and bottom by 2, we get 2/4, and then multiply the top and bottom by 2 again to get 4/8. That was a result of cutting each half in half into 2 pieces, and then cutting each fourth in half into 2 pieces. Of course, we could skip from the 1/2 up to the 4/8 if we multiplied the top and bottom by 4. Sort of a shortcut for what I actually did with the marker. All right, so we're going to go one more time, again cutting in half. What we have up there now are eighths. We have line segments that are each 1/8 long, and we've numbered them from 1/8, 2/8, and so on, all the way up to 8/8, which is 1 whole. And now I'm going to put a point halfway between at the midpoint of each of those eighths line segments. And to save time, I'm not going to use a ruler. I think I'll be able to eyeball it pretty well. A point here, and here, and here, 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 and there, and one more right there. So we had an eighths number line. We divided each eighth into 2 equally sized pieces. So what kind of a number line do we have now? 16ths, right? 8 times 2 is 16. So let's count them and name them. 0 is 0/16. The first 16th to the right of 0 is 1/16. The second 16th to the right of 0 is 2/16, and then 3/16, 4/16, 5/16. Please notice that some of these points have other names. Some of the points that I'm identifying as 16ths are fourths, some are eighths, and this one right here is 1/2. Some of the points are just going to be sixteenths, but others of them have already been identified as a certain eighth or fourth or half. After 5/16 comes 6/16, and then 7/16, and then 8/16. There's that observation we made before. Remember that 1/2, the fraction 1/2, any fraction where the numerator is half of the denominator is equal to 1/2. 8 is half of 16, and it's the same as 1/2. Then comes 9/16, 10/16, 11/16, 12/16, 13/16, 14/16, 15/16, and of course 1 is 16/16. There are a lot of equivalent fractions there now. We'll look at a few of them. How about this one here, 4/16? Well, what's equivalent to 4/16? 2/8, 1/4. You know, what we said about 1/2, you can actually say a similar thing about any fraction. With this point here, which was originally 1/4 and then became 2/8 and then became 4/16, any fraction that is equal to 1/4, the numerator is 1/4 of the denominator, right? 1 is 1/4 of 4. 2 is 1/4 of 8. 4 is 1/4 of 16. Let's see how we can sort of get to the 4/16 from the 1/4. Well, we can multiply the top and bottom of the 1/4 by 2 to get 2/8. And that's what we did when we made the eighths number line. And then just now, I changed the eighths number line into a 16ths number line. We can multiply the top and bottom here by 2 to get 4/16. So there are the three equivalent fractions, the 1/4, the 2/8, and the 4/16. Of course, we could take a shortcut in going from 1/4 to 4/16. Rather than multiplying the top and bottom by 2 twice, we could multiply the top and bottom by 4, right? So 1/4, and then multiply the top and bottom by 4 to get 4/16. Here we have 6/16, which is equivalent to 3/8. Multiply the top and bottom of the 3/8 by 2 and get 6/16. I didn't point out, I don't think, the 2/16. 2/16 is 1/8. We can say this about 1/8 and 2/16. The numerator is 1/8 of the denominator, right? This 1 is 1/8 of 8, and this 2 is 1/8 of 16. That's why it's equivalent to 1/8. That's why 2/16 is equivalent to 1/8. All right, so 6/16 is the same as 3/8. We already talked about half. Now we have, over here we have 10/16, which is the same as 5/8. If you multiply the top and bottom of the 5/8 by 2, you get 10/16. We have 3 fractions here that are all equal to 3/4. We can say this. This might be a little bit of an advanced concept for 5th graders, but some of you can appreciate it. For all of these fractions that are equal to 3/4, the numerator is 3/4 of the denominator. If this concept is kind of going over your head a little bit, don't worry about it. It'll, as you get older and develop in your math understanding and knowledge, this will be something obvious to you. But 3 is 3/4 of 4, the 6 is 3/4 of 8, and the 12 is 3/4 of 16. This idea of 12 being 3/4 of 16 is actually something I haven't taught you yet, but I will this year. So if it's confusing now, it'll be something you can appreciate by the end of 5th grade, certainly. With the 3/4, we could multiply the top and bottom by 2 to get 6/8. This one here. Multiply the top and bottom there by 2 to get 12/16, or Just like before, we could take a shortcut, start from the 3/4, multiply the top and bottom by 4 to get to the 12/16. All right, and the reason we go times 2, multiply the top and bottom by 2, and then by 2 again, that reflects the actual thing that I did with the ruler and the marker of dividing dividing each fourth into 2 pieces to get eighths, and then dividing each eighth into 2 pieces to get 16ths. That's why these are 2s. All right. We've got 14/16, which is the same as 7/8. Multiply the top and bottom of the 7/8 by 2 to get the 14/16. And I've been indicating it in that direction. But of course, ladies and gentlemen, you can go in the other direction as well. Let's say you have 14/16. You might know that there's something you can do there called reducing the fraction. And I talked about that in the previous video where the word reducing could be a little bit misleading because we're not making the number smaller. We're actually keeping it exactly the same. The numerator and denominator are each getting smaller. That's why we use the word reduce. But we're putting an equal sign here, meaning that whatever we put over here is going to be the exact same number as this one. It's not going to be lower or reduced. Only the parts of it are being reduced. And you probably learned about reducing or as I like to call it, simplifying, because then you avoid that whole confusion with reducing. Simplifying the 14/16, you probably learned that you can divide the top and bottom by 2. And there's nothing wrong with that. It works, it's legitimate. 14 divided by 2 is 7, 16 divided by 2 is 8. So there you have the 14/16 being the same point on the number line as the 7/8. You can show it geometrically, like I did here. There it is, 7/8, and it's also 14/16. You can do it just symbolically with the symbolism of fractions. But you should be able to connect the two in your minds. Or even, if I gave you 14/16, asked you to simplify, and you told me it was 7/8, could you draw a quick sketch? You wouldn't have to take as long as I did. Could you draw a quick sketch of a number line to show that they're the same point on the number line? You should be able to. This is how most people learn to simplify a fraction, by dividing the top and bottom by the same number. But as I did in a previous video, I would like to suggest this. Think of this 14/16 as 7 times 2 over 8 times 2. That raised dot there, by the way, is multiplication. I could have put an X there, but and we still will use X's to indicate multiplication in 5th grade, but we learn other ways of representing multiplication. That's not a decimal point. It's not down here. It's raised up in the middle, and it means multiplication. Well, what the formula tells us is that we can cancel those 2 2's. We could just go like that, and then we have the 7/8. And by canceling those 2 2's there, it's equivalent to dividing the top and bottom by 2. So this, what you learned of dividing the top and bottom by the same number, is not wrong, but I would like you to understand it in these terms as well, because then that's how the formula works. So in other words, we have A over B, and we multiply the top and bottom of the A over B by C. The C in this case was the 2's here, and that's equal to A over B. A times C, and when the A and the C are right next to each other, the B and the C are right next to each other, that's also multiplication. One of the things that we learn in 5th grade is different ways to represent things that we've learned about when we're younger. These 2 C's could be canceled to leave us just with the A over B. This is the all-important formula for equivalent fractions, and I've attempted here to illustrate how it works with a very specific case of halves, fourths, eighths, and 16ths, each time putting a point right in the middle of a line segment. Divide in half again, divide in half again, divide in half again. And again, that doesn't have to be done that way, but I thought it would be valuable to show you because it's very common in a situation that your parents' generation, your grandparents' generation, for many, many generations in the past, people became familiar with this kind of a number line from a ruler, not on the metric side. The metric side works differently. The metric side, and most of the rest of the world uses the metric system. The metric system doesn't divide in half and in half again, half again. What it does is it divides into 10, 10 again, or just divide into 100 equally sized pieces or 1,000 equally sized pieces. The metric system uses 10, 100, and 1,000 for its pieces. Not 2, not 4, not 8, not 3, but 10, 100, 1,000. And one of the reasons the metric system was invented and why it became so popular is it's easy to work with the numbers when they're divided into pieces of 10, pieces of 100, pieces of 1,000, which you will come to learn in your time here at St. John's, perhaps in both science class as well as in math class. So we're not going to talk anymore right now about the metric system, but in the old system of measurement with inches, feet, yards, miles, it was traditional to take each inch. Okay, now you can first see, I think you can kind of see here, you've got a 0 and then you've got a 12. The distance between that 0 and that 12 is 1 foot, and the 1 foot has been divided into 12 equally sized pieces that we call what? Inches, right? So a foot is a 12th number line. But what I was focusing on here is what's done between 2 consecutive inches, between, say, 0 inches and 1 inch. The tradition there is not to divide into 12 equally sized pieces, but to divide into halves, and then fourths, and then eighths, and then sixteenths to measure more accurately. You might, if you're a carpenter and you're cutting a 2x4, you might have to cut it into, 8.5 inches, a small 2x4, 8.5 inches. But what if you need to be more accurate? What if you actually need, rather than 8.5, what if you needed to be 8 3/8? Well, the ruler provides you a way to do that, because what a standard ruler does between each inch is it's divided into 16 equally sized pieces. Now they make some of these lines on here, these little lines that indicate, I used points. They use little lines here because you can't really put a point on the edge of the ruler, right? And the lines are of different lengths to kind of guide you. The fourths are 1 length, the eighths are a little shorter than the fourths, and the 16ths are the smallest that are there. But let me see if I can, will this work? Can you see that well enough? Might as well use the 0 and the 1 like up on the board. And so what this is, think of this as just a magnified or blown up inch, right? So let me see. You got 0 here, and then I'm going to count each of the little, each line, the really small ones, the medium-sized ones, and the big ones. Each of those little lines, as I go from one to the next, is a 16th. Let me see. 1 16th, 2 16ths, 3 16ths, 4 16ths, 5 16ths, 6 16ths, 7 16ths, 8 16ths. At 8 16ths, I'm halfway. I'm at 1/2, halfway from 0 to 1. 9 16ths, 10 16ths, 11 16ths, 12 16ths, 13/16, 14/16, 15/16, and 16/16 by the time I get to 1. So I chose to show you the 16th number line because it's very traditional on a ruler. And maybe my example of a carpenter cutting a 2x4 wasn't the best example. There are certain situations, in the past anyway, maybe now it's done more with a metric system, but there used to be situations where somebody working in what's called a machine shop, where, say, something is made out of metal or plastic, and it has to be very, very accurate in how long it is. Well, in situations like that, it was important in the past, if you were going to work in a machine shop and be able to understand the various measurements, it was important to understand, for example, that 3/8 is less than 7/16. You need to make something 3/8 of an inch. Okay. Well, maybe it needs to be a little bit bigger. Maybe it needs to be 7/16. Well, you would have to understand how equivalent fractions work to realize that this is a bigger measurement. Why is 7/16 bigger than 3/8? Here's why. Because 3/8, if we multiply the top and bottom of the 3/8 by 2, we get 6/16, right? Times 2 times 2, 6/16. And 6/16 is obviously less than or smaller than 7/16. Just to give you an idea of the fact that math can be practical. There were many people in our past, maybe not so much now or going forward, maybe because America will switch to the metric system and has switched to the metric system to some degree, or maybe it's automated by computer and the people working don't have to understand the equivalent fractions as much as people in the past that would be working in those machine shops. But this used to be something that math that would be learned in school and then would have a practical application out in the real world of work. I think I've mentioned before that next time you're riding in your car with your family and you go over a bridge, that bridge could not have been built without math. Computers could not have been built without math. This is a kind of math we learn about in 5th grade, equivalent fractions, that has real-world applications. So I hope you've enjoyed this video on equivalent fractions and that you continue to enjoy learning about math in 5th grade and beyond. Take care for now. See you soon.